When one looks at the vast space of the universe with its planets, stars, and galaxies, one fundamental question needs clarification. Why is there something and nothing? The puzzle deepens when we consider the symmetry of the physical laws that govern our universe, which seem to treat matter and antimatter equally. However, we find that the stars and galaxies we see are composed mostly of matter, with almost no antimatter. It makes us think about the complex forces that organize asymmetry and create the world as we perceive it. What deep mechanisms change the balance and give us a universe full of galaxies, stars, and the mystery of our own existence? How did this immeasurable universe come into being? Scientists have believed for centuries that the universe is eternal and unchanging, governed by immutable laws of physics. But in 1927, Belgian priest and scientist Georges Lemaitre proposed another idea. He proposed that the universe began with a large, pregnant protoatom that exploded to give birth to the smaller atoms we see today. Although Lemaitre's idea initially received little attention, the astronomer Edwin Hubble discovered in 1929 that the universe is not static, but is actually expanding. This revelation has led some scientists to speculate that as we rewind the history of the universe, it shrinks back into a small, dense point. Astronomer Fred Hoyle derisively called this concept the Big Bang Theory, which was later adopted by its proponents. The underlying suspicion persisted, but in the mid-1960s, astronomers Arno Penzias and Robert Wilson encountered the cosmic microwave background radiation, the echo of the Big Bang, while trying to tune the microwave signals of the Milky Way. If the Big Bang Theory is true, how did it lead to the formation of planets, stars, and galaxies? Accurate calculations and observations with telescopes on Earth and space probes give us the best explanation. About 13.8 billion years ago, all the matter in the universe erupted from a single, infinitesimal singularity in a violent explosion. This expansion occurred at an astonishing rate, doubling every 10 to minus 34 seconds, creating space as it rapidly filled in a fraction of a second. Gravity arose and other fundamental forces and energy transformed into particles of matter and antimatter, most of which annihilated each other. Fortunately, some of the matter survived and produced protons and neutrons within the first second. Shortly thereafter, these particles began to fuse together to form hydrogen and helium nuclei. About 300,000 years later, atoms began to form as nuclei captured electrons and filled the universe with clouds of hydrogen and helium. About 380,000 years after the original explosion, the universe left behind a remnant, the cosmic microwave background radiation, which Penzias and Wilson accidentally detected. This radiation contained small fluctuations of matter that extended to cosmic scales during inflation, eventually functioning as the seeds for the formation of galaxies and galaxy clusters as we know them today. When we look at the vastness of the universe, close observations point to a consistently coherent story of inherent uncertainties. Our universe is composed of matter and follows unchanging laws of physics throughout space and time. It operates under general relativity, expanding, cooling, and compressing dynamics, influenced by dark energy, dark matter, and complemented by normal matter, neutrinos, and radiation. In this cosmos we find galaxies, stars, planets, heavy elements, and even intelligent life, at least in one corner. These cosmic structures did not exist from the beginning, but were created during cosmic evolution, in a major achievement of 20th century scientific reasoning. Scientists have reconstructed a timeline detailing how our universe went from a largely uniform and uncomplicated state of mostly hydrogen and helium to the diverse and complex universe we see today. If we start from our present perspective, we face the question: how did each individual structure or component come into being? We repeatedly investigate the origins of each ingredient and delve deeper until we reach the limit of our understanding. Yet, even in the midst of this uncertainty, we contemplate the birth of existence. Could everything we see come from nothing? Life as we know it comes from the tiny particles that make up the fabric of our reality. These particles join together into complex molecules, the building blocks of life, which are made up of even smaller units called atoms. But atoms did not materialize ex nihilo at the beginning of the universe, but went through a long process of formation. This process unfolds in the cosmic drama of the life cycles of the stars. Stars are born, live their celestial lives, and finally perish, catalyzing the creation of new materials through cataclysmic processes. These materials in turn promote the birth of successive generations of stars and continue the cosmic cycle. This complex interaction maintains the conditions necessary for planet formation and the complex chemistry necessary for life. Several key events had to happen for the universe to manifest in its current form. Gravity orchestrated the joining together of groups of stars and galaxies, which required a primordial mass that gravitational forces could carve into larger structures. Dark matter played a crucial role in preventing matter from spreading during the cosmic formation. In addition, a delicate balance of different forms of matter and radiation was necessary for the formation of cosmic remnants, such as the cosmic microwave background radiation and the elementary components of galaxies. Central to this story is the mystery of the asymmetry of matter and antimatter. Matter and antimatter should exist equally in the primordial melting pot of the early universe, but matter dominates in our cosmos. Various hypotheses try to explain this difference, including scenarios where the usual laws of physics are temporarily discarded, creating conditions that favor the creation of matter. Prominent among these is the concept of CP violation interactions in the standard model of particle physics. When we consider the origins of our universe, we are faced with a profound mystery. Did the universe really come from nothing? While uncertainty remains, our continued quest for understanding continues to unravel the complex tapestry of cosmic evolution, probing the depths of existence itself. The universe begins with these profound questions that push the limits of our understanding.
Dark matter, despite its elusive nature, is crucial to understanding the cosmos. Although it cannot be composed of particles described in the standard model of physics, several theories speculate about its origin. It may have formed early in the warm phase of the universe and continued through later cosmic ages. Alternatively, it may have occurred during phase transitions as the universe expanded and cooled. Other hypotheses point to its existence as a new type of neutrino or as a consequence of gravity, which produces exceptionally heavy particles. The question then becomes, why does dark matter exist today when the early universe seemed to function without it? The creation of dark matter requires a thorough study of its source. One interesting possibility stems from cosmic inflation, our leading theory of the pre-Big Bang origin of the universe. Cosmic inflation suggests that before the hot Big Bang, the universe experienced a rapid phase of expansion driven by the incredibly high energy density associated with the cosmos itself. When the inflation stopped, this energy caused the formation of matter, antimatter, and radiation, which laid the foundation for the further development of the cosmos. In particular, inflation predicts certain patterns of density variation that are consistent with observation and provide strong support for its validity. Although cosmic inflation provides a framework for understanding the birth of the universe, it does invite philosophical reflection. Can we really understand a state without space, time, and the laws of physics? From a philosophical perspective, emptiness can be considered the absence of these basic elements. But from a scientific perspective, defining the void becomes a complex undertaking. Scientifically, we can define nothing in several different ways. A time when nothing existed, empty space-time with minimal energy, or the absence of the universe and the laws that govern it. While certain definitions may suggest the creation of the universe out of nothing, others question a true void without space-time and physical laws. In the field of physics, the struggle to create space out of nothing raises profound questions. How can space and time arise from a space that has no definition of place or duration? The puzzle deepens when we look at the origin of the laws that govern the universe. Without a clear framework to describe existence outside our universe, the concept of absolute nothingness remains elusive. Finally, while scientific theories provide insight into the origins of the universe, they also highlight the limits of our understanding. The quest to unravel the mysteries of existence continues, pushing the boundaries of human knowledge and perception. Quantum theory opens up exciting possibilities regarding the nature of both fields and particles, challenging traditional notions of eternity in space-time and the laws of physics. Although certain claims may point to the creation of the universe from a state of nothingness, the certainty surrounding our cosmic origin diminishes as we move beyond physical limitations. Many scientists believe that the universe could have come from nothing. This idea, rooted in quantum theory, revolves around the concept that quantum fluctuations can spontaneously create the universe. But in the absence of mathematical foundations, this idea remains speculative. Recent breakthroughs by Don Page and his team at the Wuhan Institute of Physics and Mathematics have made significant progress, providing the first mathematical proof that quantum fluctuations could be the cause of the Big Bang. Key to their success is the Wheeler-DeWitt equation and Heisenberg's uncertainty principle. The Wheeler-DeWitt equation, the cornerstone of quantum gravity, unifies quantum mechanics and general relativity, albeit without time. At the same time, Heisenberg's uncertainty principle explains the transient nature of particles in a vacuum, where particles momentarily appear and disappear into the void as a result of random quantum fluctuations. By combining these principles, Page and his team showed that a small true vacuum bubble can rapidly expand, possibly leading to the creation of our universe. This mathematical framework is consistent with observations and suggests a viable mechanism for the creation of the universe. However, it is important to note that the concept of a universe emerging from nothing does not imply the absence of physical laws or constructs. It involves a non-deterministic quantum fluctuation that leads to a true vacuum bubble in empty space, a concept intricately related to the spontaneous appearance and destruction of particles in the quantum vacuum. This groundbreaking research addresses a long-standing question: can something come from nothing? The answer depends on the interpretation of void in this context. Although a true void implies the absence of matter, space, and time, the spontaneous formation of a true vacuum bubble in an empty universe is consistent with modern scientific understanding. This concept redefines our understanding of the origin of the universe and aligns with the idea that even in an apparent vacuum there is the potential for cosmic birth. Page's work highlights the dynamic nature of the cosmos, where deep quantum principles shape our reality. It takes us into a new world of contemplation, bridges the gap between the philosophical and the scientific, and offers fascinating glimpses into the enigmatic origins of our existence.